and welcome back to Chemistry 3120, Advanced Organic Chemistry. So today we're going to start chapter 23 in the textbook. It's a chapter focused on chemoselectivity, and it's broken up into a number of different sections. So probably I'll be making around 4 to 5 to 6 different videos for this chapter. All right, so this is lecture 2. And the focus of today will be chemoselectivity and introduction to protecting groups. Just to give you a little bit of a roadmap of where we're going with this chapter, today, as I mentioned, we'll talk about chemoselectivity, we'll look at protecting groups today, introduction to them. Specifically, we'll be looking at acetals as protecting groups. Next time, we'll look at alcohol protecting groups. And then there's going to be a focus on reductions and oxidations. Okay, so before I start introducing some material, I just want to highlight some reasons why we want to study organic chemistry, why it's important for us to learn reactions and the importance of understanding chemoselectivity. So organic reactions have many uses in society. For example, medicinal chemistry, pharmaceutical chemistry. As our population ages, as we understand more about diseases, we need to be able to synthesize different types of compounds in order to meet the demands of the health and disease. So, medicinal chemistry. Materials chemistry is also a big thing in today's society, being able to design and synthesize a variety of different constructs that could have interesting materials applications. Okay, so these can range from things like polymers to what's on the surface of vehicles. Those things are very, very important. So those are just some highlights of why it's very important. Chemoselectivity. So let's go through a particular reaction. I want to introduce to you what chemoselectivity is. So let's say we do this, we have the starting material and we add one equivalent of acetic anhydride and then some base. So my question to you is, what is the final product going to look like, and what's a major final product going to look like? So before we do that, let's first identify what our nucleophile and what our electrophile is. So in our starting material, you can see here that the nitrogen has a lone pair of electrons. The oxygen here has 2 sets of electrons. These are both nucleophiles. When we look at what this is going to react with, this is called acetic anhydride. This is our electrophilic position, and this is also our electrophilic position. The reason we know this is because you have a carbonyl group here. There's a dipole moment moving this way, making this carbon a little more electrophilic compared to a carbon without a dipole. So during this reaction, there's 2 scenarios. You could have the nitrogen attack here, or you could have the hydroxyl group attack. So what do you think is going to happen? So if you treat this carefully with one equivalent, let's think about the strength of these nucleophiles. So what I'm going to draw for you, or give you, is the electronegativity scale going from carbon, nitrogen, oxygen, fluorine of a periodic table. If we look at electronegativity, we know that as we approach fluorine, that our electronegativity increases. In fact, fluorine is the most electronegative element, and that's assigned 3.0 on the Linus Pauling scale. Oxygen is less electronegative, but it's still pretty electronegative, 3.5. And then as we go from right to left, nitrogen is around 3.0, followed by carbon of around 2.5. So which element is more electronegative? It's oxygen. So what does this tell us? This tells us that oxygen is more willing to keep electrons within its atomic shell. In contrast, nitrogen is less electronegative and it's more willing to donate its electrons. So in terms of electronegativity and correlating that to nucleophilic strength, the nitrogen is a stronger nucleophile. So what will happen is that you'll get the nitrogen attacking this carbonyl group here. Doesn't matter which one because it's symmetrical. And then the electrons will come up. You'll form a tetrahedral intermediate, similar to what we had done in the previous lecture. Come back, then you do proton transfer, come back down, and you'll release off your leaving group. So your product is actually going to look like this. Okay, so that's your final product, your major product. All right, so let's take a look at another related or similar example. So what if we take a molecule that looks like this, and treat it with the same type of reactive substrate, so the acetic anhydride and the triethylamine base. So if we do this reaction, we have now two hydroxyl groups. So in terms of their electronegativity, they are equivalent. So they're going to have similar nucleophilic strength, you might think. And if you were to do this reaction again with one equivalent, you might suspect that you would get an equal mixture of reaction at this hydroxyl group and then reaction at that hydroxyl group. However, if you look at these different hydroxyl groups, this hydroxyl group is a primary hydroxyl group. It's less sterically hindered, whereas this hydroxyl group here is a tertiary hydroxyl group. It's more sterically hindered. So even though they have the same electronegativity, this one is easier to react, more nucleophilic, because there's less stuff around it. It's less sterically hindered. So this is going to be the stronger nucleophile. Stronger nucleophile because it's a primary alcohol. So if you do this reaction, you will get this as your major product. All right, so that's great. So we understand how we can fine-tune reactivity. We understand different nucleophile strengths if we're doing particular reactions based on things like sterics and electronegativity. But what if you wanted to make actually the reverse product? What if you actually wanted to acetylate at this tertiary hydroxyl group, but not at that group? Or what if you wanted to acetylate at the hydroxyl group here, but not the amine group? How can we overcome the inherent reactivity differences in organic chemistry? So this involves a concept called protecting group chemistry. So what are protecting groups? All right, so protecting groups are ubiquitous in organic chemistry. We use them routinely to mask the reactivity of a particular functional group while doing a particular transformation on another protecting group. So I'll give you an example of some protecting groups, but before we do that, let's first define what protecting groups are. So protecting group is a functional group that with another group to make it inactive. So in our case, we're looking at nucleophiles. So if we're looking at this molecule here, and if we don't want the primary hydroxyl group to react, we protect it with a protecting group. So you can think of this as a general scheme. If you have, let's say you have molecule AB, and you want B to react, but A is more nucleophilic, what you're going to do is you're going to protect functional group A with a protecting group and not touch functional group B. So we call this the installation of the protecting group. After we do this transformation, we now do our desired transformation of whatever B to X is. So in these cases up here, we're going from an alcohol to an ester. So B to X, so the desired transformation. And then finally, we need to go back and remove that protecting group and go back to original functional group A. So this is your general scheme of how a protecting group works, and you're going to apply this type of mindset for a variety of different organic molecules. There are three general criteria that are important for protecting groups. So number one, the protecting group installation must be very easy, high yielding, and fast. You don't want to do a sluggish reaction. You don't want to be waiting a long time. So you want this to be a very robust reaction that is reproducible in the field. Okay, number two, your protecting group must be resistant to the conditions for the transformation. So obviously you don't want your protecting group to come off or to cross-react with whatever conditions you're using. So the protecting group must be inert to the desired transformation conditions. And then number three, the protecting group needs to be removed, but you want to make sure that you can do this very easily and in a high yielding manner. So you don't want to be spending a lot of time trying to figure out how to remove that protecting group. So it's important to remember, protecting groups have to go on easily, but also of equal importance, they have to come off easily too. So I just say protecting group removal must be easy and high yielding. Okay, so if we, maybe let's look at this example here and say, well, let's actually figure out how we could make this as our major product. Where you have the amine unreacted and you have the ester here from that hydroxyl group. So in terms of using a protecting group strategy, and I won't go into specific chemicals, I'll just outline the steps that we would take in order to generate this. The first thing you would do is you would protect the amine. With a protecting group. And we'll learn lots of different types of protecting groups for alcohols, aldehydes, amines, so on and so forth. Secondly, you'll do the desired transformation. In this case, this is the acetic anhydride with the triethylamine, right? And then the last step is going to be removal of that protecting group. Once you learn different protecting groups and different strategies to take them off and understand their inherent strengths in terms of what they're stable to, what they are labile to, what they come off with, then it's very simple to put in which protecting groups you'll use and what conditions to deprotect them. All right, so the first thing we're going to do is look at protection of the carbonyl group. In particular, we're going to look at protection of the aldehydes and ketones. But before we do that, let's look at carbonyl groups in general. Okay, so the protection of the carbonyl group. All right, so I'm going to draw 4 different carbonyl groups that are ubiquitous in organic chemistry that we use a fair bit. So this is our good friend, the aldehyde. This is now going to be a ketone. This is an ester, and this is that's an amide. Okay, so all these carbonyl groups have some type of dipole moving electron density up to that oxygen. And you understand that because oxygen is more electronegative than carbon. So there's a natural dipole, meaning that there is a resonance structure where you have some positive character at this carbon and negative charge at this oxygen. So you can do this for all these different carbonyl derivatives and draw appropriate resonance structures. Okay, now let's take a look at how positive or how electrophilic these groups are relative to one another. And let's start at this amide here. Here's the resonance structure of the amide. We've drawn a positive charge here. But recall back to our periodic table, electronegativity scale, which I erased, but that's okay. I'll redraw it right up here. Carbon, nitrogen, oxygen, fluorine. So your nitrogen, okay, is not as electronegative as oxygen. So if you think of the electrons here, they're actually more willing to donate electrons. And we learned that when we looked at that first example. So what's going to happen is you're going to have actually pretty strong resonance character where the nitrogen can donate electrons and you move that positive charge to the nitrogen. Don't forget your formal charge rules. Nitrogen here has 4 bonds, positive charge. If we do this and look at this compound here, this is an ester. We have an oxygen here. Oxygen is more electronegative compared to nitrogen. However, it's still willing to donate electron density. Not as strong as nitrogen, but it's still willing to contribute. So this would be a resonance structure, another resonance structure of that ester. If we look at the ketone, this R group is some carbon chain, and there are no free electrons on the carbon, so there's no way to add electron density. You will have some electron cloud and some van der Waals interaction with this positive charge that will stabilize it, but it's going to be much less compared to these two resonance structures from the ester and the amide. And then finally, the hydrogen here of the aldehyde is actually really, really super small, and it's not going to be able to donate to any significant degree to this positive charge. So as we go from left to right, think of electrophilic strength. Which molecules are the most electrophilic? Well, the aldehyde is the most electrophilic, right? Because this positive charge cannot be shielded from the particular group here. Ketones are also very electrophilic, but it's not as reactive as aldehydes because you can get more electron clouds interacting with that positive charge. So as we go from left to right, you decrease your electrophilicity. And you also increase the stability of these compounds. So amides are inherently very stable compounds. You've probably heard before, perhaps in biochemistry, amide bonds have this double bond character to them. What they're exactly meaning is this double bond from the nitrogen because it's so willing to donate through resonance. So increase your stability as you go from left to right. So therefore, the compounds, carbonyl compounds that often require the most protection are things like aldehydes and ketones, and not so much esters. We'll talk about those later, but these two compounds definitely require protection. So we're going to talk about the protection of aldehydes, and it would also apply to ketones as well. Okay, so let's look at acetal protection, or more specifically, it is a protecting group, but let's call it acetal formation. From an aldehyde. Okay, so pretend you have a molecule that has an aldehyde, and then there might be an ester and an amide on there, and maybe you want the ester to react with a nucleophile, but you need to protect that aldehyde because it's so electrophilic. So let's go through this protection, and what we're going to do is we're going to treat this with an alcohol, and we're going to use catalytic amounts of acid. And the acid that we'll use is para-toluene sulfonic acid. So para-toluene sulfonic acid looks like this. And we often abbreviate this as para-toluene sulfonic acid. All right, so I've told you that these are inherently electrophilic compounds. However, in order for this reaction to proceed much faster and to very good yields, we need to add that catalytic acid to activate the aldehyde. So I'm just going to show how this happens. Here's your catalytic acid. And the carbonyl group has a couple sets of electrons on the oxygen. So what you're going to do is you're going to transfer a proton to the carbonyl group from the para-toluene sulfonic acid. And what that's going to do is that's going to make a positively charged species that's higher in energy, and it's going to be more reactive to the alcohol. I know this because if I draw that resonance structure like I've done previously up there, what you can see is that I now have a positive carbocation, as I've shown here. So that's your electrophilic center. So at this stage here, your alcohol can come and it can attack the carbocation. Now there's two ways that you can denote this. You can show the alcohol group attacking this oxonium species and then electrons going up, or if you draw the resonance structure, you can show the electrons coming and reacting at that positive carbocation. Doesn't matter which one you use. Perhaps for this first one, since I've drawn the carbocation, I'll have it reacting right here as I'm showing. All right, so once that reacts, you will now have your alcohol group attached. Your oxygen now has 3 bonds, so don't forget your formal charge rules. This is positive. And then let's think of the first proton transfer event we had. During that reaction, this was the acid and it became the conjugate base. So now the conjugate base of para-toluene sulfonic acid looks like this. And now the conjugate base is very happy to come and pick up that proton from this oxonium ion. Recall here that the pK of this is quite low. It's around -2. So it's fairly acidic. That's very willing to pick it up. Okay, so once that happens, we now generate this molecule here, which is called a hemiacetal, which represents a protected form of the aldehyde. If you were to do this reaction and have one equivalent of the alcohol, that would be your product. However, to push this reaction, we actually saturate this reaction with a large excess of this alcohol compared to the equivalent of the starting material. So we're going to keep going with this reaction. So at this stage here, what you're going to do is you're going to say, well, this OH here is actually a very poor leaving group. We're under acidic conditions. So how can we make this a better leaving group? So again, let's take our acid. In this case, I'm going to use our abbreviation. And the OH group is going to come pick up the proton from para-toluene sulfonic acid to generate OH2+. That's positively charged. That's a really good leaving group. And then what's going to happen is that the oxygen from the alcohol that reacted in previous steps is going to undergo something called assisted ionization. So this is called assisted ionization step. Where a double bond's formed and then you get release of this good leaving group, water. Remember, we are under acidic conditions, so you can't have OH minus leaving. You can have things like water leaving. So now we have this molecule here, right, which is an oxonium species. You can see here that if you move electrons up here, you now would have a resonance stabilized carbocation. This looks very similar to the same activated aldehyde that we started with. All right, it looks very similar. So it's going to react in the same way. So in this case here, I'm going to have the second molecule of our alcohol. Remember, we are in large excess. This is going to come react at that carbon center. You now have your oxygen there positively charged, and then we need to remove this proton, and we can use the conjugate base from paratoluene sulfonic acid again. So the O- will come, remove that, and then what you are left with is this protected form, which is an acetal. And that's your, that's your final product when you take an aldehyde with lots of equivalents of alcohol, catalytic paratoluene sulfonic acid. Protect that as an acetal. Couple points I want to make. Notice that the acid that you use is catalytic. In the first step, it's donating a proton to this carbonyl group. And then later, you can see here that it actually picks back up the proton after the alcohol reacts. So first donates, conjugate base picks it back up. Then it goes through another cycle in which now the alcohol group here picks up a proton. That allows this to leave as water. And then after the second alcohol comes and attacks the conjugate base of paratoluene sulfonic acid, removes a proton. Or picks up the proton. So the paratoluene sulfonic acid is catalytic. You just need a very small amount, and it's really acting as a proton shuttle during this reaction. It's neither consumed or used during the reaction. The other thing I want to point out too is that during this reaction, all these steps are actually reversible. Okay, but we force equilibrium to the acetal because we have a large excess of the alcohol. So what I would like you to think about is the deprotection conditions, right? How would we deprotect this molecule? Because eventually we want to go from the acetal back to the aldehyde. All right, so I want you to think about that for homework, and that concludes today's lecture. See you next time.